Astronomers have been using optical telescopes for over 4 centuries, but they like thinking out of the box, and innovation has taken astronomy far beyond its historical realm of visible wavelengths. In the history of astronomy, there have really only been 2 major revolutions in the way we view the universe. The first was the invention of the telescope, first used systematically by Galileo to observe the night sky, and subsequent to that, the gradual growth in the size of collecting area to gain this factor of 10 billion in depth over the naked eye. The second revolution in astronomy, equally important, was the levering open of the electromagnetic spectrum by technologies that allowed us to detect radio waves, infrared waves, X-rays, gamma rays, and ultraviolet radiation, often from the same astrophysical object. These technologies took a while to be worked into serious and mature radio facilities, X-ray facilities, and gamma ray facilities, but now we have ways to probe the universe across the full range of the electromagnetic spectrum. Perhaps the final frontier in this history would be opening up the universe to gravity waves, which essentially give us gravity eyes and let us see the mass of the universe directly. Remember that electromagnetic radiation is sometimes an indirect way of seeing the universe because it depends on the ways that light reflects, refracts, and emits from normal matter. We don't see the matter itself. With gravity waves, we would see the stuff of the universe directly, and this may be the final frontier in astronomy. As a prelude to seeing the stuff of the universe, astronomers have experimented with using the universe itself as a telescope. Einstein's general theory of relativity contained a core prediction that mass would bend space, and that light would follow the contours of the curved space and so be bent by matter. This is called gravitational lensing. The gravitational lensing effect, where mass literally acts the way an optical lens would by focusing and magnifying and distorting radiation, has been observed now thousands of times. The typical situation would be when a massive cluster of galaxies, containing the equivalent of perhaps 10 to the power 15 stars, sits between us and more distant galaxies. That huge concentration of matter bends light such that the distant galaxies appear magnified, amplified, and distorted by the foreground cluster. The cluster is acting essentially as a lens. The lensing effect, the amount of the deflection, is a key to how much mass that cluster contains. So this is a way of weighing the universe or objects within it. A simulation shows the effect. The foreground lensing object is made of massive red galaxies like elliptical galaxies. The background, more distant young galaxies are blue, and their light is sheared and distorted into miniature arcs. These little arcs, which exist in fragments that form concentric circles around the center of the mass distribution causing the lensing, is a classic signature of lensing, cannot be mistaken for any other phenomenon. In a simulation, it's easy to show what would happen if we move the lens across the sky and observe its distorting effect on different background galaxies. Hubble Space Telescope was the first facility that showed this effect strongly and clearly with its exquisite imaging, and Hubble itself has now seen this effect hundreds of times. A single deep image of a cluster of galaxies with the Hubble Space Telescope shows the dozens of red, relatively nearby galaxies in the cluster, and literally hundreds of distant background galaxies, more blue, that are distorted into tiny little fragments and arcs. Each of these little distorted fragments is like a ray tracing in an optical diagram, and this entire configuration gives us a wonderful measurement of the mass distribution of that object, the cluster of galaxies causing the lensing. Along the way, of course, we're confirming Einstein's general theory of relativity, since this was a core prediction of the theory that was unobserved when Einstein made the prediction. Astronomers have moved beyond vision to new ways of seeing the universe. The first was just an assistance to the eye, the optical telescope, larger and larger gathering power to amplify what the eye could see. More profound was the revolution that opened up the electromagnetic spectrum, a factor of 1 trillion in wavelength. And more recent is the prospect of looking at the universe in terms of its mass, either by the detection of gravity waves or by the use of the universe as a telescope through the gravitational lensing effect.